And hi, everyone. Welcome to the second to last CCOM-OE seminar for the spring semester. We're grateful to have Dr. Stephanie Ordóñez Sánchez here with us today. She's going to talk about ocean renewable energy technologies. She is a mechanical engineer from Mexico, interested in developing sustainable solutions to meet our growing energy demands. She currently works at the University of Strathclyde as a Chancellor's Fellow. Her line of research is focused on the offshore renewable energy sector, and particularly undertaking experimental research in marine energy converters to analyze performance and dynamic loading. She is a member of the technical committees of the European Wave and Tidal Energy and the Pan American Marine Energy Conferences. She encourages young females to study STEM areas through her involvement in the U.S.-Mexico Foundation Initiative, Mujeres Líderes en STEM, and now through the Homeward Bound Initiative. She enjoys walking her two dachshunds, swimming, and running. For this presentation, you may ask questions during the presentation by unmuting yourself, or you can also enter in the chat and I will read it aloud for you. With that, Dr. Ordóñez Sánchez, you can share your screen and begin your presentation.
Okay. Oh, no, this is not the one. Okay. Oh, are you seeing my screen? No.
Yep, we can see your screen.
Ah, yeah. Oh, but not the presentation.
We see part of it, just not presenting yet. There you go.
Like that.
Yep, perfect.
Yeah. Sorry. Thanks, Nicole.
No problem.
Thank you very much. First of all, for inviting me to give this talk. I didn't realize actually my camera is here and I'm giving the presentation this way, so it's not that I'm not seeing you. Apologies for that. Yeah, today I'm going to talk about the research that I've been doing at the Energy Systems Research Unit at the University of Strathclyde. As Nicole said, I'm going to stop halfway through the presentation in case everyone has a question, but please unmute yourselves at any time, and I'm happy to discuss anything that arises during the presentation. So I'm going to talk first a little bit about Glasgow. So as Nicole said, I'm from Mexico, and I came to Glasgow 14 years ago to do a PhD in marine renewables. And since then I stay here. So Glasgow is a very vibrant city, actually, for the people who have never been here. It always rains, and this image basically seems to be like a lie because it's very sunny and there's no people. But as you might imagine, we just finished our 4 month of lockdown, so the high streets were like this, completely empty. And well, this is the place where I work. So this is where the Department of Mechanical and Aerospace is in the city center. It's very close to the city center. And basically the Department of Mechanical and Aerospace Engineering at the University of Glasgow divides into 4 main areas, which is energy, aerospace, fluids, and materials. So basically I'm part of the Energy Systems Research Unit, where part of it is about marine renewables and other part is about energy transition, energy vectors. So there's a lot of research regarding hydrogen as well, energy storage, and all these aspects. But today I'm just going to focus on marine renewables. And the content of my presentation, so basically this is the work that I've been doing in collaboration with a lot of people. And it's a lot of projects I've been involved with in the last few years. And also I'm going to touch a little bit on another subject, which is women in STEM, which is something that is a very exciting initiative that I'm involved in. And I think a lot of, I can see like a good example there, Nicole and Coral, who invited me to this topic. I'm sure they will be exciting to be part of something like this. So that's why I want to put a bit of time there. So, okay, so I guess picture summarizes what I basically do. So I do my research in, as I said, in marine renewables. It's pretty much experimental analysis of optimization of rotodynamic performance of tidal stream turbines, but also looking at the structural reliability of the devices. No, as some of you know, and from what I've heard about, I think most of you are in the ocean sciences or engineering. There's a few ways that we can convert the energy from the tidal stream or currents to a mechanical, electrical energy, right? So I work primarily with the horizontal axis turbines, three-bladed ones, and basically we've used a few different ones to assess aspects like dynamic loading and performance, changing the blades, trying to modify them to meet different aspects of what we're trying to achieve. Well, this is basically what I'm going to talk about. I'm going to start first with a project that we had with a researcher that now it's actually in NREL. So Dr. Murray, she did her PhD in Dalhousie, but also in collaboration with Strathclyde University. So basically what she did was to do a model to test bend twist couple blades. And the idea is basically that instead of having a normal rigid, I don't know, carbon fiber blade or aluminum blade, basically what we are allowing is to try to allowing the blades to flap and twist a bit on purpose. So basically in that way, we are trying to shed the load, so to increase the reliability and I guess the life of the blade, but without losing a lot of power. So she did this model and came up with a design of the blade. And then we tested it at Strathclyde University in the Kelvin hydrodynamics tow tank. And basically this is one of the graphs that we got. So what we have here is basically on the darker points, we can have the data from the composite plate. So this is data coming from the thrust. So the whole loading on the full rotor, against what we did with some aluminum and rigid plates. And we also did that for turbulence and wave current, but I will talk about this a little later. So basically this is the setting that we had for the experiments. As I said, we had a three-bladed turbine. So this was a while back. And what we had here is basically in this case, the stanchion was the one that was it had strain gauges. So basically, we calibrated the stanchion with at the tow tank. So basically, applying some loads and obviously this is not the best way to do it. But at that time, we didn't have a load cell on the rotor itself. But it just gave us a good indication of what the turbines were doing. And to extract or to obtain the data from the torque. So basically what is giving us, power is torque and angular velocity. So we needed the torque data, and this was taken from the motor generating current. So basically the extra current that the rotor was developing. No? So here is a snapshot of a photograph of the composite plates. So we tested both the aluminum and the composite blades. And you can see here the blades that are unloaded, and here are the loaded blades. You can see a bit of deflection, which is what we expected. And this is basically just the time and the data sets that we were getting and how we were comparing them, and use that data to show you the average values over the whole spectrum of the operation of the turbine. So for those of you who are not very familiar with the characteristic curves of the turbines, basically what we get is two common curves, which are coefficient of performance and coefficient of thrust. So basically these two graphs indicate us what's the operation from the full. So same as, for example, a pump in your house or something like that, no? So from when the turbine is completely loaded, so from when it is completely freewheeling, so when you don't put any load on it and you just let it rotate with the flow stream, or when you start extracting the energy. So those are the characteristic curves that we usually get from these turbines. And this is something that I will show you in a bit. So this is some of the initial work that we did with Robin about her bent twist coupled blades. So these are some blades that were, they just were epoxy, and it had filled with epoxy, and it was just some carbon fiber plate. Then we wanted to look at how these blades were operating when they were operating in wave current interactions. So for this, but also with turbulence. So for this, the Kelvin hydrodynamics tank was not the best, because obviously you don't have any turbulence, although you have a very clean wave that you can create, as some of you might know in the tank that you have in your university. So basically, we went to Ifremer, and this is basically the parameters that we use. Ifremer is a facility that it's in France. I don't know if you guys are familiar with it, but it's in a very nice place called Boulogne-sur-Mer. That if you go, you have really nice French food. So basically, the parameters that we were trying to characterize the turbine with were different wave heights, different levels of turbulence, and the different flow speeds. But actually, I guess this is something that we have learned with the time, no? So at that time, at Ifremer, there was not a lot of experiments done with waves, and actually the limitations of the tank when you do waves and currents there is a bit limited. So we had to set our parameters to a flow speed of 0.8 meters per second, a very, very small wave height of 0.15 meters, and a frequency of 0.5 hertz. So at big scales, it's actually, I think, only, I don't remember. I think maybe 1 meter of wave height or something like that. It's not much. But anyway, that gave us a bit of an insight of what was what we wanted to get out of it. Again, we want to look at the loading, the dynamic loadings on the rotor, but also the change of performance that we can get from a rigid blade compared to a bent twist coupled blade. And you can see here, so that the turbine is only 0.8 meter in rotor diameter. And at that time, at Ifremer, they have this LDB. So basically, it's an instrument that allows you to measure the velocity of the flow, and you can get different data out of it, right? You can get flow turbulence characteristics, the flow speed, and basically you can correlate to what happens with the flow and what you're getting out of the turbine. Now, we actually was quite far from the turbine. We did a characterization with and without the turbine, but we also had the LDB working all the time. And this might not seem the best approach, because the LDB was quite far away from the rotor, but it was something that we were testing, as in trying not to affect actually the flows when they were very close by the turbine. And this is something, and I will discuss a little bit more later, because it's something that maybe some of people working in marine renewables have encountered, that there's not really a lot of best practices of how to go around these issues. So anyway, these are the results that we got. So basically, you can tell again that you get the lower thrust using the composite blades and a bit more with the aluminum blades. And these are the data that we get actually from the wave current interaction. So basically, what we were looking at is for every wave period, we were looking at the changes and the fluctuations of the thrust and torque, and we do get obviously the low levels of the thrust range, so maximum minus minimum of the dynamic loadings were lower when you look at the composite blades, but also the torque. And I think it was very difficult to actually see the advantages of the composite blades at such low velocities, because we did some other experiments at higher velocities, and we could see more the changes, no, on the torque, on the thrust, sorry. So how we were shedding the thrust loading from the rotor blade. We didn't do more experiments on that, because I think at that point Robin hadn't finished her PhD and she was afraid that we were going to break her plates. So we stopped there, but I think that gave us a good parameters of what else we could do. We continue work with Robin. Now she works at NREL, and I will present a bit more on that. So she now works with thermoplastics. So that's another area of work that we're looking at in currently. So well, that was a bit from the bend twist coupled blades. Oops. And now I'm going to talk a little bit of hydrodynamic loading on this composite, well, composite and yeah, composite or plates. It could be rigid and composite plates. So basically, this is something that we wanted as well in parallel from what Robin was doing, and also to feed into a project that was called ARICASM at that time. It was basically funded by EPSRC, one of the organisms here in the UK. And basically what we wanted to do is to try to do a pressure map of the blade of how the fluid affected the stresses on the blade. No? So now you can do that obviously with computational fluid dynamics, which is very expensive. And so basically, yeah, so we instead of using computational fluid dynamics or as a 3D large simulations or stuff like that, what we try to do is to couple blade element momentum theory with CFD. So for those of you who are not familiar with blade element momentum theory, it's a very simple analytical technique where you can actually get the performance of the blade through the computation of thrust and torque. So it's based on conservation of momentum, and basically you discretize the annular section of the rotor in various segments, no? And you feed the model with some aerodynamic coefficients of lift and drag that you can get from, well, usually what we do is get it from wind tunnel, but ideally it would be from a flume or something else. I don't know if you guys actually, maybe you do that, because I think in the US you get more funds than what we do in the UK. But anyway, so this is another area that that we were looking at, and what we did is basically so get this pressure distribution along the blade, and we compare this. Roughly, we verify it with this. We loaded the blade, and we were getting some surface strain mapping. So this was done in collaboration with Newcastle. They had this the surface strain mapping techniques, and we were just comparing a bit roughly what we were getting in the model and what we were getting in this carbon fiber blade that we had from ages ago when we were testing a turbine that was developed at Strathclyde University. So I'm not sure if you guys are familiar with a contra-rotating marine current turbine. It's called Cormac. Sorry. And then, so basically we did that work with Newcastle, and we came up with these models. And I think, well, they look nice, no? I don't know if this is very useful, but they look at the different pressure distribution along the blade. So basically this is a hollow blade with a structural support, you can see here. And what we are fitting into the model is a regular wave, and it's only 2.6 meters of wave height and a period of 6.1 seconds. We did a more extreme case, which is again the same blade, but this is under 10 meter of wave height and a wave period of 10.06 seconds. So obviously this helps you to look at more like fatigue analysis of blades and looking at different compositions of materials, no, like glass fiber, carbon fiber, different layers, different directionality of the fibers, and so on. And basically what I was telling you about was an extension of this work that it's been done with NREL and Cardiff University as well. So we were looking at the use of thermoplastic resins, and this is basically just to improve the saturated properties, and it can get the mechanical properties can be recovered after being dried, and also the recyclability of the blades. So there's a lot of now life cycle assessment, carbon footprint, and what we can do with this when basically the lifetime of the blades expires. No, so there's actually some work in Strathclyde University of one of my colleagues who's looking at the recyclability of carbon and glass fibers. But this is something that we are doing with Robin, and in fact we were going to test some of these blades, but COVID situation happened, and now we have stopped a lot of our experiments that we had planned for last year. But anyway, that's my excuse. And well, I'm going to talk now a little bit about this project that we had in collaboration with Cardiff University. It was a 4-year project called Dilota, and basically it's called dynamic loadings in tidal string turbines. So the idea of this project is basically, again, assessing dynamic loadings and of an array of turbines, actually. So for this project, we had 3 turbines, again, horizontal axis turbines. We developed this blade, which is based on a Warman cross-section, and again, three bladed rotors, but differently from the turbine that I presented before. This is better instrumented. So basically what you can see in this diagram, we have a load cell here that measures thrust and torque behind the rotor. So, and again, we try to avoid any parasitic loads of friction or so, try to get as real data as possible. We have all the buses where the structure, basically where the blade sits on. They are also instrumented with strain gauges. And we are measuring here axial and tangential forces for each of the blades. Now, we also have the encoder, and we are able to use the 2 control strategies. So speed control and torque control, which is something that we also wanted to look at in this project. So we have some, well, we did actually a lot of experiments with a single turbine, just looking at looking at a single turbine. And this is the tow tank actually in Italy. I don't know if you guys have heard of it. So it's actually, sorry, on the left-hand side is the turbine installed at Incian. So it's a tow tank, a very big tow tank in Rome. So it has 9 meters in width and 3.5 meters in depth. And we were looking at actually very large wave heights, a bit of extreme conditions on their speed and torque control. And on the right-hand side, we have the same turbine at Ifremer. So in this one, again, you can see here the waves that we were creating. Again, I mean, obviously there's advantages and disadvantages of using these 2 facilities. No, on the one hand, you get more realistic flows on the flume rather than in the tow tank. But then again, you have some limitations in the flume tank that you don't have such a clean data than what you get in the tow tank. But I guess it really depends what you want to get out of it. So for this, what we were looking and we wanted to look at is the average thrust loading that we will get from these 2 facilities. So basically here in these graphs, you can see the average thrust range that we will get with speed and torque control strategies. And basically what we found is we've got higher fluctuations of the thrust when we have a torque control strategy on the regular waves. And I think that's because it's the turbine obviously doesn't have a set velocity, and you can get this increase in the angle of attack at all points during the rotation of the turbine. And here are just some images of the maximum and minimum thrust loading that you get as well, and the average thrust range according to the wave height. Again, we see as we were expecting, we see an average thrust range increasing with the wave height, but also this was seeing much more with the torque control, and these are at the same operating conditions. This is another aspect that we were looking at, which is the phase difference. So basically we saw a phase difference between the surface elevation, so the wave, and the thrust loading. And what it was interesting, so obviously we get the phase difference in both for both techniques of the torque and the speed control. But we see a slight I think a smaller difference of 5 to 10 degree phase difference with the torque control. And again, that's important because I think if maybe at some point there's we have, well, I've tried in some cases to understand what happens with the rotor if you get all the data from, let's say, a wave gauge or so. So if you can actually infer the data from the other oceanographic parameters, so on a wave or turbulence or so. And I think this phase difference might be quite relevant to try to match these, to correlate these loadings and this time series. So this is well, this was part that, sorry, of what we got in the in Ephemer and in the tow tanks, or tow tank and plume tanks, sorry. And this is the last, well, kind of the last part that we were able to do. So this was some array interactions that we wanted to do. This is in the Flowway facility in Edinburgh University. So for those of you who have not seen it, so basically it's a massive pool of 20 meters of diameter. So I think this section, the section of where you test is 10 meters or so, but you can get, you know, the currents from all the directions, wave from all directions. And it all sounds very good, but actually when you try to do a test there is it's a nightmare, because the flows, they are really hectic. So we did a bit of testing to look at the lateral spacing, downstream spacing between turbines to see what are the wake effects. And this is relevant because obviously when you go into the field and you want to install a lot of tidal turbines in an area, you want to maximize the power output, but also you want to reduce the amount of loading that you get in the turbines. No? So that is something that we were trying to look at. For example, if we put the turbines closer together, then you get a higher acceleration between the turbines, but that is going to maybe affect this one. There's studies that show that they increase the power output, but also obviously the structural integrity of the turbine is damaged. No, so this is. I put the other video because here you can obviously you can't see anything. And well, some of this data we are going to present it at UTech. I don't know if some of you are familiar with it. The people who are in the renewable energy or offshore renewable section, you might be. So this is going to be presented in September, the results from this data. So I'm not going to talk more about this. And before I jump into the next topic, I don't know if you guys have any questions, because I'm aware that I'm running out of time. So just in case you want to comment something or have questions or so.
If there are any questions written in the chat, I'll read it aloud. Okay. It looks like you can continue with your presentation. We'll wait until the end.
Okay.
Thank
you. I think
you.
I'm being very clear.
Yes, you are being very clear.
Okay, so now I'm jumping into another topic, which is about round robin testing. And this is a European project that we have with a lot of universities. Some of them are Ephemer, the Conseil CNR in Italy, Edinburgh University, Queen's, Belfast. And what we're trying to do in Marinet, for those of you again who are not in the area of marine renewables, basically this project is about facilitating access to a lot of facilities in Europe from everywhere. So basically, even if you are in the US and you want to go and test at some of the tanks that I've shown, you can put your application and obviously your proposal has been reviewed and you can get access. But it's not only about access, it's also about training, because there's some online training courses. And I guess the research aspect of this Marinet project is about round robin testing. And it's round robin testing of different concepts. So it's wave energy, offshore wind, tidal energy, and components. So it could be mooring lines, electrical cables, etc. And the part that I'm more involved in is the round robin testing. So basically, what we're trying to do is use the same turbine and take it to different tanks, put the same parameters, and test if there's an influence from the facility into the results that you obtain. And also look at the best practices or establish any best practices. As I said before, there's, I guess, because the technology is still quite new, I guess there's not certain standards that many people follow, or some people follow one and the other, and there's not really a consensus of which one is best. So this is the round robin testing. So here we are using the turbine that was developed by Ifremer, an organization in France. And in fact, this turbine is very well instrumented. So again, it has a torque thrust load cell behind the rotor, but here we have the instrumentation. I think each blade root it has a 5-axis sensor to get a better comprehensive analysis of the blade root bending moments and forces. And again, so what we did with this testing was also to have the turbine, the same turbine in all facilities, but also the same equipment as like the wave probes, at least one wave probe, at least the ADB was going to come as well to all the facilities to test the same program. And basically, I forgot to put the diagram of the instrumentation that we had, but basically it's similar to what I've shown before. And these are all the cases that we tested. So we tested 2 current-only cases, but also we tested as well waves, regular waves, and an irregular wave. And basically, this is the flow characterization of 3 facilities. So again, we haven't been able to finish the testing because of COVID. But you can see here the test that we have done at Ifremer and a tow tank at Italy and at a flow wave facility. And you can see here, so these are basically the profile, the water column, the velocities at the water column of each of them. And obviously from the tow tank where you don't have any turbulence effects or so, you can see that basically what we did, it was to put the ADB and run the towing, the carriage, to get these points without the turbine in place. And then we set the same ADB in flow wave and in the other facility, and you can see here the massive fluctuations that we get obviously at the flumes, like Ifremer and flow wave. So this was the first part of the testing, and obviously we wanted to look at the operational curve. So what we said, I said before, it was the CP and CT curve, so performance of coefficient of performance and thrust coefficient. And basically what we've seen is actually a quite similar data, average data, if we were looking at the whole data sets. And we can see a bit of difference with the flow wave facility. And I think the problem with flow wave, so basically there's something that we use that is called blockage correction. Maybe some of you have heard it. So basically, we account for what's the dimensions of the tank, the cross section against the size of the turbine. So obviously, the bigger the turbine, the more you use of the tank, and basically you have a lot of effects from this blockage that you are imposing into the flow, no? And so the problem is that the same correlation or the same function that we're using to do the blockage correction for the tow tank and the flume tank in Ifremer, we are using it from flow wave, but that doesn't that might not be the same. I mean, it might not be the best approach, because obviously flow wave, you have again the same cross section, which is only 2 meters in water depth, the same as in other facilities, but it's a quite wide facility, no? So I think we have to take to learn from this and apply other blockage corrections for this type of facilities. And there's a lot of people in Oxford actually working with blockage correction factors, and it's something that I think we will do in the future. At this stage, it was basically looking at the flow characteristics, performance of thrust and the power, and look at the overall power of the device now. So I'm going to just flip through this quickly because I'm aware of the time. And just another, I guess this is important for best practices. We were looking at the uncertainty, obviously, of the data. So you can see here that, again, the data from Flowway seems to give us a bit more of uncertainty just because of the type of flows that we were getting. So again, it's not much. It's the maximum value that we got from the combined uncertainty was about 4%. So it's not much for the thrust. And in fact, a bit like 6 or 5% for the torque data. So we still need to do that for the blade data. But we also see here the convergence of the thrust data and for the whole time we were recording the data. So I think, I don't remember. Yeah, so it was at 250 for all the facilities, except for the tow tank where we actually used a reduced amount of time, just because, you know, we have steady flows. So basically, this is part of the round robin testing, and we're still looking at the data, and we are aiming to test this turbine again in the tank that we have at Strathclyde University, so finalize with another tow tank, but also taking it to another place in Ireland, Northern Ireland, which is called Portaferry. So that's where CGen, one of the most well-known turbines, was installed for 5 years or so. And they have very nice tidal stream. So we are not going to put the little turbine in these massive flows of 5 meters per second. So we are going to try to find a nice sweet spot where we get 0.81 meters per second. But again, we are not sure if this is happening due to COVID. This is almost the final topic that I want to touch base in this presentation. So we have looked as well in the last couple of years for the opportunities to develop technologies for lesser energetic flows. So as I say, I'm from Mexico, so I was very happy to do this collaboration. Basically, what we are analyzing is the Yucatan current that passes through this part of Cozumel. So for those of you who have been to Mexico and have been to Cancun, you know Cozumel Island is very close to Cancun. And it's very touristic, you know, for the people who like to dive and to snorkel. You have a lot of marine life. So, but also you have this continuous current that is not really affected by the tide. And we wanted to see what would be the possibility of using this current to meet the demands of the Cozumel Island. So even though Cozumel Island doesn't have a lot of population, I think it's maybe 500,000 people, maybe less, they receive a lot of tourists, and they could be even 2 million people coming to the island at some point. And obviously, the only source of energy that they have is a cable that runs from a mainland to the island, and the rest is produced by diesel generators. So obviously, it's not very good for the environment. So this is a project that we did in collaboration with Mexico, and basically we were looking at the so basically the guys at Mexico, they did some transects with an ADCP, but only the snapshot. So looking at the spatial variability of the flow from south to north, to basically find the best spot where we can get these currents, no, and when we could extract energy. So basically, these are some of the transects that the guys were looking at from south to north, and you can see here that in this part of the island is where you have the best flows. And actually, you get quite decent bathymetry. The topography of the floor is quite nice. So we did a bit more of analysis and tried to see, take the profiles that they got us and assess the performance of a 3-bladed horizontal axis turbine and quite a small turbine to see what would be the benefit of going there. So this is an ongoing project as well. So this was just the first part, and we are just waiting for some fund to come over to continue with this second part of the project. And just to show you a little bit of the resource that we have from the ocean currents to the tidal flow. So this is data from tidal site in Orkney in the north of Scotland compared to the ocean current. So basically, obviously, we get a higher percentage of occurrence of a flow, even though it's quite small, the velocity, or quite low the velocity. It's only 1 meter per second compared to what you can get in a tidal site, which is 3 meters per second. But when we were looking at the annual energy on this is capacity factor, we get a capacity factor of quite high, which is about 70% compared to a tidal device that is only maybe 30 to 40%. So obviously there's opportunities there for the people of Cozumel to use this energy. And we were looking at some aspects of how, what would be the best rotor diameter that we could use to minimize the cost, the levelized cost of energy. And you can see here, I'm really running late, but I will finish in a minute. So basically, we can see that for an ocean current, we have basically the sweet spot would be working with turbine diameters of 5 to 10 meters, according to an initial evaluation. So basically, we have done a lot of assumptions for this. And basically for the tidal stream, for a tidal site, it's better to work in maybe a region of 10 to maybe 17 meters of rotor diameter. So basically what is now being commercialized. And then I'll just go very quickly through this because I really want to go to the last slide. So basically another thing that we are looking at is looking at the clean water demands with tidal energy. So instead of converting the energy to an electrical load, what we want to do is to use that rotor dynamic energy to go into directly, I guess, feed into a high pressure pump to drive a reverse osmosis module and so basically not using this tidal technology to produce electrical energy, but to produce clean water demands. So that is something that I'm doing with Delft University. And this is some initial data that we're going to present at UTEC again. So what we find is that for a 10-meter turbine, tidal turbine, we can provide a clean water for about 2,800 households using an average household rate of 349 liters a day. And just to finalize, sorry, just very quickly, I really wanted to mention this because I think it's really important, especially for all the women that are here that are very good in science. So I've been involved in this initiative called Homeward Bound. So it's an Australian initiative, and it's basically to empower women that work in STEM subjects, but also to provide, to help to combat climate change. So it's a 12-month leadership course. It's open to basically any women above, I don't know, 20 years old who's working or who's doing the university or PhD or whatever, but it has to be related to STEM, and it's even better if it's related to climate change and all these aspects and environment. And basically you apply, and it's an amazing experience. So basically what the initiative is trying to do is to build up a network of I think it's 100 people over 10 years to build up a network of 1,000 women, to empower them to be in key role positions, to give our points in climate change and what the strategies should be. So here I provided a link where you can see basically the video of what Homeward Bound is about, or you can all ask me questions about this if you want afterwards, because it's a great opportunity for you guys. If you're interested, I'm part of the 6 cohorts, so there's going to be 4 more cohorts. And the amazing news, and I think that's really what you would be interested. So basically it's a 12 leadership course and it ends up in Antarctica. So hopefully, the COVID provided, I will be going to Antarctica next year in 2022. And sorry for running out of time. This is me. Thank you very much. And you can reach me by email or Twitter or whatever. Thank you.
Thank you so much for that presentation. That was really interesting, getting to see all the different projects that you've been a part of and learning about Homeward Bound. I'm definitely interested in that, and I'll probably email you more about that later. If anyone has any questions, feel free to unmute yourself and ask directly, or you can type it into the chat and I will read it aloud for you. We have a presentation in the chat, or a question in the chat. It says, great presentation. Can you speak a bit about how you estimated the LCOEs for different turbine sizes? Example, assumptions, limitations.
Yeah, of course. So basically, obviously, we looked at the capital, operational cost, annual energy. So the bit that I'm very, very comfortable about is the use of our data from the rotor, from our rotors, to use actual CPs, the generator sets, and everything to get the annual output and annual energy output, and also some of the, obviously, the data coming from the sites, no? So the tidal side and the ocean current side, that's data that we provided from IMEC, actually the European Marine Energy Center, and from Mexico. For all the other assumptions, for all the other bits about capital and operational costs, to be honest, what we did is a review of basically the literature that is available for LCOE analysis, and look at the different geometries of our rotor sizes and try to come up with just equations basically of how best to assess the capital cost compared to the rotor sizes. So that's one part for the capital cost. For the operational cost, that's even more complicated. And to be honest, that's that it was something that it was taken from the National Renewable Laboratories. They have a good database, and it was basically more difficult because we were trying to compare an ocean current device to a tidal stream device. And obviously the operation is going to be different, especially because we are working at very low velocities in the ocean side, but also more constant. No, it's not like the tidal side that it could change a lot. So that is something that we did. So it's a very, very crude analysis, but it was just for us to give a sense check of, because now so I didn't mention the second part of the project with Mexico is actually to build a prototype to put it in the Cozumel channel. And that's just to give us an indication of what should be the scale device or the real size device, because as we can see, the real size could be a 5-meter diameter or a 20-meter diameter, no? So yeah.
Thank you. Any other questions?
Yeah, I'd like to ask a question. Yeah, very nice overview presentation of all the different work you're doing. Very nice. You skipped beyond one. You skipped very quickly past one slide that I think nicely illustrated the difference of working in towing tanks versus flumes, and how very little scatter you have in the data in towing tanks, and how much scatter there is when you introduce increasing levels of turbulence. Could you? Oh yeah, thanks. If you want to go back and do you know what I mean?
I think.
Yeah, right here.
So
the round robin testing.
The round robin testing.
Go forward.
There, this one? No.
Next.
This one?
Next.
Yes.
Next.
This one.
Right. So the middle is a towing tank, and then left is the flume, right is flow wave, right?
Yeah, exactly. And
so,
yeah, and you're right. I'm sorry. Yeah.
And the top is just flow, bottom is with waves. Is that correct, or what's the difference there?
No. Actually, yeah. Well, so top. Sorry, is the surface elevation. So basically, the wave, the flow that we have captured with the wave. So wave current interaction, if you want to see it that way. Obviously, in the tow tank, we don't have that interaction, so it's pretty much the flow velocities. And here is actually what you could do is a variation of the flow with this. So it's basically just this fluctuating part of the flow in the ephemer and the flow wave. But it's not. But I guess it has the surface elevation. But we were using the ADB. So basically, it's just we're taking only the fluctuating part to show how much the spread is in the flow and in the tow tank.
Yeah, thanks. So it's a bit different from what I thought it was, but yeah, clearly you can see that there are no waves in the tow tank. Okay.
And yeah, and actually, yeah, sorry.
But how come you have velocity fluctuations in the tow tank? Is that?
Yeah, I was going to actually say that we actually think, you know, what we did in the tow tank is again, it's maybe not the best approach. We put a tube in front of the ADB, and basically we pierce the tube and feed the particles, right? So they would come, but the particles settle so quickly. So I don't know if you guys have a better way of doing this, or if you do it. And what we are seeing here is probably more the vibration of the carriage rather than the flow, as you were saying, the fluctuations. So in fact, we are not very happy with the way we did the tow tank flow analysis. And that's something we want to repeat in the Kelvin hydrodynamics lab when we have the opportunity. So if you have a better way of maybe you guys do it, please share it with me, because
you can try hollow glass spheres. They're if you buy them at they come in different sizes. The 11 micrometer size is almost neutrally buoyant, so they actually stay. They don't settle out or float that fast. Hollow glass spheres. I'll put it in the chat.
Thank you very much. Yeah, we will try that. We're still working on when we will be able to do the testing, but I think maybe that's something we can try out. Thanks a lot.
Someone in the chat just said, great presentation, Steph.
Thank you very much.
Are there any other questions? Those are your dachshunds, I'm assuming.
The dog had a question.
I'm sorry. Yep. They actually, you know, they behave very well for almost 1 hour. Sorry.
Yes.
It was deemed
yeah,
to happen.
we did not hear them at all. All right, but if there are no more questions, that will conclude the presentation. I just want to say thank you again so much for preparing for this. It really was excellent. And we have our last seminar next week, so please be on the lookout for an email about that. And I hope everyone has a great weekend. Thank you.
Thank you very much, everyone. Thanks, Nicole and Coral, for organizing.
Of course. All right. Bye, everyone.
And yeah, and get in touch with me in case you want to hear more about the homeward bound stuff, or
yes,
or now
definitely.
it's very up to you. Yeah.
Yeah. If anyone is interested in the homeward bound stuff, they can stay on while we chat about that. If they're
yeah. I'm happy to stay a couple of minutes more if that's something that is relevant to you.
Yeah, definitely. So can you tell me more about that? Because it was a very brief. Oh yeah, someone wants the link for the homeward bound project in the chat.
Yeah. I can share that with you. And Jimena left, so there was another participant from the homeward bound. I think she's the one that said that was a good presentation.
Oh, okay.
So I think it's because we are homeward bound colleagues, and she wanted to support me. So I'll share it now. So basically, yeah, I'm very sorry. I wanted to talk more about it, and there's a very nice YouTube video in the presentation. I don't know if I can give you my presentation and you can see the link.
I can share that with everyone via email, or we can have it like live on your. We have a web page, and you have a permanent place on that page in the seminar section. So I will add that to that, or have that added.
Okay. I will put it here. I just found it so very quickly. So basically, as I said, it's a program. It's an Australian initiative, really done for female with a STEM background. The idea is that you work in some topics about climate change or environment, but not everyone does it. So there's a lot of people from the medical sciences and stuff. But the idea is that basically every year, now I think it's been delayed because of COVID, but basically every year they open the call, and you submit your application with a video of what had been your challenges, you know, and the different leadership, I guess, positions that you have taken along your path. And they might select you, they might not select you. It's a bit competitive. So I think there was 500 applicants from when I submitted my proposal, and 100 of us were selected. But you get like really a very big network of people doing their PhDs until people that are in retirement positions, and that they've been, like, I don't know, there's a people from the European Commission that is, it's in a very top level. So I think the network that you build up is really, really interesting. It's something that I've taken a lot from this program. But also, as I said, it lasts for 11 months. And we have basically sessions of 1 hour and a half, 2 hours every 2 sessions every month. And they talk about leadership values, what's your leadership journey, what are, shaping you, as if you've never taken a leadership training. This is really a very good one. I've never taken one, and I'm amazed about it. They talk you through, things that you've never considered. They come up with this. So I really like it. And every time you get some homework, the stuff that you have to reflect upon and stuff. And then basically the end is that you have to come up with, well, I guess there's another aspect of it, which is challenging. Basically, they fund you to partially the program and the trip to Antarctica, but you have to come up with the other 50%. So basically, you have to come up with £20,000. So you have to do all these crowdfunding activities. So now I have a lot of crowdfunding activities with people in the UK and with people from Mexico. So it's 4 Mexicans that were selected, and that's interesting bit, right? Because you have to go with companies and ask if they are interested in, for example, for you to give them a talk, or families and friends asking for money, or the university itself, if they are willing to support you. And then you get all this visibility throughout all these different aspects. So that's basically the program. It just started for me in March, so it will finish in March next year. And then the trip to Antarctica, I think it will happen next year in November or so.
Okay, and that trip happens every year? Is that typically?
Typically, yes. So now I think for the homeward bound, the cohort, the HB5, it's overdue, because they were supposed to go November last year. And now I think they will go, they say November next year, but obviously it's all up in the air a bit. So normally, yes.
Okay, and is that just to meet everyone in person, or is it like a conference, or?
So basically, yeah, it's to meet everyone in face to face, because you've been online with them for the last 11 months. So it's to bring everyone together, but the leadership course continues. So the journey to Antarctica is 3 weeks, starting from Ushuaia, Argentina, right? So that's what they tell us. So I think it starts from there when you meet, and then along the trip, you basically continue with the leadership training. And obviously they take you, I think, to research centers as well there, so to see what other people are doing in Antarctica. Antarctica is because it's the most fragile environment that we have, and where we see the effects of climate change more faster, no? So that's the idea of going there and see. For me, it's also very interesting because I'm in a lot in the energy transition and energy vector. So it's the way that, these people basically meet their demands. No, what do they do? How do they, go around with the waste and food? And it's possibly one of the most sustainable communities that you can find on Earth. So I think that's very interesting.
Yeah, that'll be really interesting. Thank you so much for sharing that. Does anyone have any other questions about that? No. Hi, Melissa.
Hi, my name is Melissa. I just had a quick question about that program. So when would you apply? You said you're in from March to March, so if we were interested, does that make sense?
Yes, at the moment, I don't know if the new, the call has been open for the HB7, because obviously they have not even, there's everything up there with us. So I don't think they want to commit to another cohort. But they have a Facebook page, and they have a few other channels where you can, so you can get the newsletter kind of thing. And, when the stuff comes up, then, basically try to reflect about leadership, what you have been doing, challenges that you have had, because you will need to do a 2-minute video, which sounds easy to do, but it's really complicated. I think I started and I was like, I'll take my video. And the first one I did was 40 minutes. I was like, okay, far off of what I have to do. So, you know, you have to start, you know, thinking about these questions. And I think it's a good opportunity. And if you don't get it, then you apply for next year. It's nothing stops, you know.
Right.
So,
Awesome.
Cool,
yeah.
cool. It definitely sounds interesting. So I'll keep tabs on it, I guess is the best way to go about it.
Yeah, exactly. Yeah, I wanted to share with you because I'm sure it's fascinating for a lot of people. So yeah.
Yeah, definitely. And I haven't heard of it, so I appreciate you mentioning that.
Yeah, no worries. And if you have more questions, just let me know. I'm happy to
All right.
help.
Sounds great. Thank you so much.
Too.
All right.
Okay. Well, yeah. Thank you very much for the invitation. And yeah.
All right.
Yeah.
Have a great weekend.
Yeah. You too, guys. Take care and enjoy your Friday.
Thanks. Bye.